Okay, let's try this and see what happens. So a little review of kinematics, and then into forces. So this unit we're doing is dynamics, which, as you can see there, is the study of motion and the forces that cause motion. Last year, you sort of separated the two out. You looked first at just kinematics, which is the study of motion without reference to the causes of motion. So that's mainly what we're doing here right now, is we're looking at kinematics, or sort of a review of that. First thing we need to review and make sure everybody is really solid with is a vector versus a scalar. So remember, a vector is a mathematical quantity having both magnitude, which is just a number, right, and a direction. So for example, 10 meters east, right? That's a vector because it has a magnitude 10, and a direction, which in this case is east. It doesn't have to be north, south, east, west. It could be a bearing. It could be just above the horizontal, or anything like that, anything that gives you some indication of the direction. The way we represent vectors, or show this, is arrows. The arrow points in the direction of the vector, assuming on paper you can show it that way. And the magnitude we try to represent with the length. Obviously, in a lot of cases, it's not to scale, or it just can't be. But the relative proportions should be consistent. And trying to draw diagrams this way when you're solving problems can be quite helpful. You're not always bang on, but it's still helpful, and it helps you interpret your results. So you can see the examples I have here below. A represents a vector 25 kilometers east. I usually draw east to the right on the paper. And B represents 50 kilometers west. Right? So it's in the opposite direction, and it's twice the length, or roughly twice the length. And if you're writing something that's a vector, remember to put the little arrow above it. So you can see here both A and B have those vector symbols above them. And that gives us some definitions, which is what we like in physics, right? Understanding what a vector is and how it's different from a scalar, we can define quantities more precisely. So for example, we can say position is a vector, right? It's some point in space relative to some origin. So you can define what the origin is. The point you're calling 0, 0 is arbitrary, and it's up to you. But it just note it as a vector, even if it's just you're using just a positive negative system, right? If it's position, it's technically a vector. Distance, the second one here, is just how far an object moves, no matter the direction it moves in. So you just basically add up however far you move, and that's your total distance. Displacement, that's the third one there, that's delta D. And if you remember, everybody remembers this delta symbol right here. That just means change, right? The change in position. And that is, so to get that mathematically, you just take the final position and subtract whatever the initial position is, right? If you were initially 5 meters away from the point 0, 0 and you went to 7 meters, right, your displacement is positive 2. That's it. Okay. So I will look here at a practical example. An object starts out 1 kilometer east of the school. It moves 4 kilometers east, then 3 kilometers north. Determine the final position, distance, and displacement of the object. So you can see here where a diagram is helpful. We can say, okay, here's the school. And this is kind of our point 0, 0, if you will. And it starts out 1 kilometer east. So we'll put here. Right, here's our start. There we go. It moves 4 kilometers east. So it goes, let's say here. And then it goes 3 kilometers north. And it ends up here. Right? We could assign the numbers to these positions, I don't think, right? So technically it starts out at, we'll see if we're using a coordinate system. I could say this starts out at 1, 0, right? The x would be 1. And then it goes to this point here, which would be 5, 0. And then it goes up 3, so it would end up at 5, 3. So first we wanted to figure out its final position. Right? Now you could write this really, I would just write it as the point that its final position is 5, 3. You could do sort of the whole vector calculation for this relative to the school, but this is the point relative to the school, right? Relative to the point, we've assigned the value 0, 0. We're saying that's our origin. Next, and I didn't label these A, B, and C, but just why not? The distance that this thing travels, right? This is the scalar, right? We don't care about what direction we're traveling at any point in time. So first, this thing goes 4. East doesn't matter, just the fact that it goes 4. Then it goes 3 relative to where it starts. So that means the total distance is just 4 plus 3, which is 7. I guess I could put meters in here for this. And finally, we want to know the displacement of the object. And for that, right, we have to look at where it finishes relative to where it starts. So for that, that's going to be the vector here, right? That's the displacement, its final position relative to its starting position. And I'm imagining you all know the 3, 4, 5 triangle, but for this, we could break this apart and we could even put in a nice angle here. And we can say, well, the displacement, now sometimes we just put bars around it like this. This just means absolute value, which means I just want the number. Or in this case, it means I just want the magnitude, right? I just want the number, not the direction of it. Because it's a vector, this means I'm only giving you the number. So in this case, it's, well, I go 4 east and 3 north. So that's just going to be the square root of 4 squared plus 3 squared, which is the square root of 25, which you all know is just 5. Then I again get this angle, right? If you're thinking about your trigonometry here, right? I'm looking at, there's my theta, there's the opposite side, there's the adjacent side. So to get the angle here, right, I could say it's the tangent of theta that's the opposite over the adjacent, which is 3 over 4. And that means I have to take the inverse tangent to figure out what the angle itself is. So that means theta is the inverse tangent of 3/4 or 0.75 if you prefer. I feel like I know that one, but the calculator says 36.9. Degrees. I'll probably use degrees exclusively in this course, so you don't have to worry about trying to do radians or anything. Therefore, I can represent the displacement, which I should have had the delta symbol there, is 5 meters. And we're going to say, so it's 36.9 degrees. So here's where I have to be very careful about the angle. Remember, this direction was east and this direction was north, which I'm using both of these as positive in my calculations. So this angle here means if I start out pointing east, right, I go 36.9 degrees toward north, right? I go in that direction. So that's the way I will report this. I will say this is east 36.9 degrees north. And that's the way I would read this. So when you look at um, a vector reported this way or the direction reported this way, the first letter is just the place you start, and then the angle tells you how far you go, and the second one is how far you go towards that one, right? So you could have reported this differently. You can, right? You could have reported this as north 63.1 east, which would be kind of the same angle, right? Roughly, you could say, no, I want to start here and I want the angle going that way. So there's always going to be some sort of complement there. But usually, I find it easiest when you do a calculation like this is to just go back to the diagram you drew and figure out, okay, where is that angle from? Like, where do I start and where do I go towards? And that'll get you there. Yeah, so just as to like the 5 3 up here, yeah, I mean I assigned a value 0 0 to the origin. Since the question was worded that way though, since it said it starts at 1 kilometer east of school, I took that to be something significant. So for that reason, when I'm reporting position, I feel like it's I should report that position relative to what some origin is, and in that sense, I would take that as something that's been provided for me. It doesn't state explicitly in this question to report the position relative to the school. If that was on a test or quiz, that's absolutely something you can ask me or like, any teacher, right? Like, do you want the position relative to the school? Because it doesn't state that here explicitly. Yeah, so for this, the process here of doing the inverse tangent, um, here that's what we had to do. But often you're given information that you actually have to break it apart. So for us, we were very fortunate in this question as the first question. I wanted to be easy because we were told 4 east and 3 north. So those are numbers that are they're perpendicular or 90 degrees, right? Same thing to each other, so you can do that really nicely. Often though, you're given a vector like delta d. In this case, you're given a vector that is 5 meters east, 36.9 north, and then if you're going to add that to some other vector, you've actually got to break it apart. So you've got to go the other way and figure out the components of that vector. Okay, moving on. Speed versus velocity, kind of the rate of change version of position and displacement. So, speed is the rate of change of distance, and velocity is the rate of change of displacement. For speed, we just use v, and for velocity, we use v with a vector symbol, right? Just to represent that it is a vector. Um, Average speed and velocity versus instantaneous. So the average speed is the total distance divided by the total time, right? In other words, v just equals d over t. You could put this as delta d over delta t if you want, but usually we're just adding up, like we did in the last problem, all the segments or whatever to get the total distance and then dividing by the total time. So if you were starting at a time that's not 0, then yes, it would just be delta t, right? It would just, if you were only doing from 5 to 10 seconds, then you'd only be dividing by 5 for time. Average velocity is the total displacement divided by the total time. So if we write that as an equation, and this time just for completeness, I'll put it in, because for displacement we were already using that. And again, I often find it somewhat unnecessary to write it all out, but you can as long as you understand what it actually means, I think is what's important. So if you just put a t or a delta t, it's not a big deal. Finally, the instantaneous velocity is the velocity at a specific instant in time. So mathematically, and I know we maybe haven't done any calculus yet, but we say it's the limit as delta t approaches zero. Um, and so what that means is if you take this equation, right, and you want to know the instantaneous velocity, conceptually, what you're saying is what is the velocity at this instant in time? Well, at an instant, time would be zero, right, which would mean you're dividing by zero. Now you can't divide by zero. So instead of saying divide by zero, what we say is, okay, well, then consider what happens as delta t gets closer and closer and closer and closer to zero, right? It gets so close to zero that it can't get any closer, right? That's what we mean by that. That's all it is. And I put that little note there because I find that an interesting thought. Is that really possible? And you probably have a sense of instantaneous speed or velocity, right? You're driving a car, you look at the speedometer, it tells you 60 kilometers an hour. You have a sense of that's my speed at this instant in time, right? It's not, you don't think of it probably as an average. You don't think, oh, over the last, zero point 0.1 seconds, that's my average speed, right? Which technically you need some delta t to calculate it, right? And so that's why I put that little like brain teaser there. Is it possible? Can you actually have even a speed at an instant, right? Don't you need some time to pass and to cover some distance in that time? How can you say at this instant? Because at this instant, aren't you stationary? Right? So it's a little more thought provoking concept than you really realize for a lot of people, I think. Um, but that's really the concept of it is just we're saying is time is so small that it's basically zero, and then we say that's instantaneous velocity. And interestingly enough, this is what you mean when you say speed or velocity, right? You mean instantaneous. So usually you're looking for the word average. If you're solving problems, look for the word average in there. So if it's not average, technically that would mean instantaneous, which is a much more difficult thing to calculate. Right? So we will use almost exclusively average, even like if we just use average over a very small time that I give you, right? Something like a millisecond or whatever. That's still not technically instantaneous, but we'll use it. Okay, I wanted just to be a little more precise since I'm looking at it. If you're looking at this equation, right, just to be very clear about delta D and delta T, that just means you're looking at D1 or D2 minus D1. If you want to use 1 and 2, you can use initial and final is fine as well. Divided by the change in time, that means T2 minus T1. In other words, I'm using those subscripts to mean at time 1 and time 2. That's exactly what this is. Sometimes it's just from zero, so it's a little easier, but technically that would be your equation. Okay, I have a problem here that sort of uses some of these concepts. So you can give this a try just on your own, sketch it out, see if you can get some of these numbers, and then it might be a little better to do it that way, and then I can take it up. And here's my solution. So as I was just saying, I can't imagine trying to do this without a diagram. Like it's just such an important part to figuring out where everything is and what's happening. So if we look at the question, right, doing the physics shuffle as I like to do, I go 2 meters east, then 4 meters east, 45 north. Sometimes that east 45 north is just reported as like northeast or whatever, right? Because it's right in the middle. And then 3 meters north, 30 degrees toward west. So we want to determine the total distance, the displacement, and I get the little blurb there. and then the average velocity if the whole trip takes 5 minutes. Okay, so yeah, so for part A, I want to say, look, here's where I start, right? And then I go 2 meters east. So here I even drew, you don't have to do these, but sometimes it can actually help right on top of the end of the arrow. So remember, it's a vector. So the first one, uh, the first one starts here and ends there. So it can actually be a little bit helpful. Sorry, let me get rid of that. Just to put that right on top of it and say, okay, then from there, the second vector starts where the first one stops, right? So that's this point right here. And then it goes 4 meters. So I tried to draw that one a little bit longer. And then it ends right here. Then I go 3 meters north, 30 degrees toward west. Let me just double down. And so that's where, again, I start pointing north and then I go 30 degrees toward west. And again, I do a nice little coordinate system right on top of that just so I can be sure of how I'm moving from that position. So those are the three blue ones that I have here, right? Those are those vectors here. So I've drawn in green the total displacement, right? So your total displacement says start, right? Start down here where you actually start and stop up here where your final position is, right? That's your total displacement, or that's what that's going to be. Okay. So anyway, for the first one, for part A, we just want the total distance. And so there's A right there, right? A is just 2 plus 4 plus 3, which is 9 meters, right? I go 2 meters, then I go 4 meters, then I go 3 meters. It doesn't matter what direction I'm going in. Even if I had backtracked, it would still be part of my distance. For part B, though, displacement is a much more complex calculation, right? I need to know exactly what my final position is relative to my starting position. So the way I would do this, particularly because I've got 3 different vectors here, I don't want to be doing triangles and doing, cosine law and all that. You can, but I find this to be the most straightforward approach is just take each vector. If it is not in a direction northeast, south, or west directly, then break it into its components. And one of the most helpful things I always find for these problems is you can always look at each direction or each dimension, if you will, independently. So the first vector, 2 meters east, I'm calling that the positive x direction, right? Is east. And I wrote that up here. So there's the positive x direction is east, the positive y direction is north. So anything that's going south, I would write that as a negative number. So the first vector, again, that's done. So the 4 meters, I have a 45-degree angle here, so I break it apart into its components. So what I'm doing over here, right, is just do a little bit of trigonometry. So what I do is I say, well, the sine of 45 degrees, so here's my angle here, right? So the sine of 45 degrees is the opposite side, which is this y component over here, divided by the hypotenuse, which is the 4 that I know. So that allows me to write this equation right here. Then multiply both sides by 4 so I can get the y component, right? The y component of this is 4 times the sine of 45 degrees. Sine of 45 degrees is 1 over root 2, or some people will say root 2 over 2, but I'm good either way. You can just use a calculator and get a decimal, but why not use an exact number if you know it? Okay. And you're going to do the same process for the x component of this vector. You're going to say, well, here's the angle that I know. I want this part right here. I want the x component of that vector. and I know that this distance, or this here, the hypotenuse of this triangle is 4. So the cosine of 45 degrees is this x component over 4, multiply both sides by 4, and that's how you end up with this right here. Cosine of 45 is also 1 over root 2, so you can replace the cos 45 as 1 over root 2. That leaves you with 4 over root 2. And in this case, that actually comes from this. That's where I got that. I set up that equation. So sometimes I do it that way. I write the trig function that I know, just so it sort of helps me figure out if I'm making sure that I'm doing it right. And then I do the same thing for this vector here that's 3 meters north, 30 degrees west. I just take the angle I know, I label it right in here, and then to get the, now it's the x component is the going to be the sine, right? That's this one here. So the sine of 30 degrees is this x component over 3. That's, you can see how I wrote the equation just to make sure I knew it, and then rearranged it for x, right? The x component that I want. And then I did the same thing for the y component. I said the cos of 30 degrees is y over 3. Rearrange that for y. You end up with this. Now, I didn't write them in here, but just so you know, the reason I have numbers like that here, cos of 30 degrees is root 3 over 2. That's why this shows up here. And the sine of 30 degrees is 1/2. So that's why this becomes that here. Also note this second one is negative because I said the positive x direction is going east. Since this is going west, I have to be careful to report this as a negative number. And so watch stuff like that when you're adding it all up. Now, to get the vector d, I can just look at the components, right? So to get the x component of d, which is this here, right? I just add the individual components. So I take, this is 2 down here, and then I've got this part right here, and then I minus that over here, right? So those are my 3 numbers, and that's exactly what shows up right here to get the x component of the displacement vector. 2 plus 4 over root 2 minus 3 over 2. And that worked out to roughly 3.3. And then to get the y component, it's the same thing. The first vector doesn't have a y component, so the y component of the first vector is there, 4 over root 2, and the y component of the second vector is right there. So that's those 2 numbers added together, and that works out to 5.4. Now I only need to consider this green vector right here, and I can say I need to know that angle. I also need to know the magnitude of that vector. So that's the first thing I do. Remember I mentioned earlier magnitude bars. So to get the magnitude of it, I just do Pythagorean theorem because now I've got the perpendicular components of that displacement. So 5.4 squared plus 3.3 squared, 6.3. So now I know the magnitude of that. So using those 2 components, I get 6.3. And then again, be careful when you're getting your angles, understand what it is. Because, and this is where the sketch is so important, right? The way I've drawn this and with my little coordinate system here, I know that angle that I'm going to find is going to be starting north and going toward east, right? And so, okay, so once you get that, and here's again where I have to be careful. I know this angle, so I know the tangent of this angle here is this opposite side divided by this adjacent side. And that gives me the numbers that I want here. And that's where I work that out. Do the inverse tangent. I get 31 degrees. Now I know I can actually report that as 6.3 because I already know the magnitude, north 31 degrees east because I know where that was from.